أعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم. This is the part 2 of the presentation on the field experience of corrosion and corrosion control in water desalination plants. This is the first slide of the part 2. It reads as sources of corrosive and erosive constituents in MEE WTP. Chlorides are a natural source of seawater. Dissolved oxygen of seawater at normal temperature and pressure. Temperature comes from steam used as heating source. MEE plants operate at relatively low temperature. Temperature has a minimal effect on corrosion rate of the metallurgy used in these plants. This slide shows the erosive and corrosive constituents in two modules, lung tube MSF WTP. Seawater source, mainly chlorides, dissolved oxygen gas, dissolved carbon dioxide gas, seawater scale forming salts, dissolved hydrogen sulfide gas, dissolved ammonia gas, dissolved bromine gas, deteriorated internal non-metallic lining in seawater intake line that leads to internal corrosion and erosion of metallic components used in seawater intake line and downstream components. Sources of erosive and corrosive constituents in two modules, long tube MSF WTP. Chlorides come from seawater. Seawater contains almost 3.5% sodium chlorides, depending on intake location. Oxygen comes with seawater. Seawater contains 8 ppm oxygen at normal temperature and pressure from feedwater pump leakages and during shutdowns. Carbon dioxide comes from decomposition of bicarbonates in seawater. Bicarbonates and sulfates are main scale-forming salts in seawater. Sources of erosive and corrosive constituents in two modules, long tube MSF WTP. This is a continuation of the previous slide. Hydrogen sulfide gas comes as a part of feedwater take from organic polluted water source. Ammonia gas comes from decomposition of hydrazine dosed to boiler feedwater to remove oxygen. Bromine gas comes from seawater intake after seawater acidification and chlorination. Sand pottery comes as a part of seawater feed and broken internal lining of the feed in intake line. Components prone to corrosion and corrosion in two modules, long tube MSF WDP. Heat exchangers, tubes internals are prone to erosion and tubes externals are prone to corrosion, gum erosion. Flash chambers are prone to corrosion based on metallurgy used in their construction. Scaling is common in these plants where tube externals develop under deposit corrosion in flash chambers. Corrosion occurs at the tube sheet and tube internals, and venting system is also prone to internal and external corrosion. Constituents causing internal corrosion in thermal two-module long tube MSF WDP, chlorides in seawater, oxygen gas in seawater, carbon dioxide from bicarbonates in seawater, hydrogen sulfide gas, bromine gas, ammonia gas, still forming components such as carbonates and sulfates cause under deposit corrosion. Constituents causing internal erosion corrosion in thermal MEE and MSF-WDP. Unfiltered solid particles in the seawater feed, high feed velocity, turbulence, and fouling in water intake. Constituents causing external erosion and erosion corrosion in thermal MEE and MSF-WDP structures. Solid particles during sandstorms inflict selective erosion of structural externals exposed to local environment, depending on the direction of the wind, its impact, wind velocity, storm intensity, and the location of these plants. Seawater condensed vapors on external surface of both MEE and MSF WDP structures threaten foundation integrity, particularly where dust and sand accumulate. Constituents causing external erosion and erosion corrosion in thermal MEE and MSF WDP structures. Seawater mist and salt-laden air are main corrosive constituents causing external corrosion to structures above ground, whereas underground structures, mainly pipelines, suffer corrosion from soil constituents when these structures are made from metallic metallurgy, even externally coated. This slide shows constituents causing corrosion of non-metallic components used in thermal MEE and MSFWDP. Non-metallic materials used in thermal water desalination plants suffer deterioration during operation. Externally exposed above-ground non-metallic components in these plants are affected by ultraviolet radiations unless coated or blended with UV-resistant components. Substandard patchwork and unqualified joining techniques are equally responsible for causing deterioration in non-metallic structures such as water intake lines. This slide shows types of corrosion observed in thermal water desalination plants. Is a uniform corrosion and its locations. Uniform corrosion is observed in carbon steel flash chambers in MSF plants and tubes externals in stage 1 to stage 4. In cross tube MSF plants in vapor condensing zone and tubes externals in stage 7 to stage 12 in MSF plants as shown in the next slide, which is actually slide number 38 of the entire presentation. Flash chambers in MSF plants were made of carbon steel as a part of original design amid concept that decarbonator and deaerator remove main corrosive constituents such as oxygen and carbon dioxide to the extent where water was likely to become non-corrosive to the carbon steel metallurgy. This slide shows the types of corrosion observed in thermal water desalination plant, a uniform corrosion location. It's a continuation of the previous slide, right, where the uniform corrosion was observed on copper nickel 9010 tube externals in stage 7 to stage 12. You can see that how bad is the corrosion, where the upper layer of the external tubes is flaking off like as a scale is being removed on a stick thread. This slides a continuation of types of corrosion observed in thermal water desalination plant. The uniform corrosion causes high degree of flashing in flash chambers, decomposition of seawater carbonates, dissolution of carbon dioxide in water to form carbonic acid. Carbonic acid causes the uniform corrosion of copper nickel 9010 rise at temperatures more than 60 degrees centigrade. The continuation of same slide is types of corrosion observed in thermal MSF WDP, controlling uniform corrosion in these water desalination plants. Uniform corrosion in flat chambers was unending process, was overcome by cladding flat chambers with AISI 316 stainless steel seam welded. Improved efficiency of the deaerator and carbonator. Maintain uniform flashing as per design. This is a continuation of the previous slides, right? How to control uniform corrosion. Replace and fasten damaged, dislocated, distorted, dislodged demisters to stop flashings reaching flash chambers. This slide shows the types of corrosion observed in the thermal MSF WDP, mainly the how to control uniform corrosion. Keep carbon dioxide concentration to level where copper nickel 9010 alloy remains immune. Improve ejectors efficiency to vent gases. The misters are made of AIS 316 stainless steel, designed to allow water vapor to pass, not water mist and water droplets. This slide shows the crevice corrosion locations in thermal MSF and MEE water desalination plants. The crevice corrosion of chains, rollers, bushings, and pins halted the use of bore screens in 4 months' time after put in service. Chain rollers and pins were made from stainless steel with 12% chromium fabricated in-house. AISI 316 components fail too, but not so frequently. Bar screens were designed to remove seaweeds, floating debris, large particles, placed upstream of the band screen in water filtration system, supplying feed water to the water desalination plants. This slide shows crevice corrosion locations in thermal MSF and MEE water desalination plants. On epoxy-coated fasteners plates in seawater filter screens in MSF plant, perforated crevices were seen on almost all tube sterners, under and adjacent to tube supports, and partition plates from stage 1 to stage 12 in 2 modules, long tube MSF plant, which is slide 48 as a part of the presentation, and actually it is a slide number you will come to know when we read to that slide. On threaded joints, joints play in thermal compression. Two evaporators, a spray film horizontal tube, MAD plant, same is as slide 47, which in fact a part of the entire presentation, but you will see it when we read to that slides in this part. This slide shows locations of crevice corrosion. as observed in thermal MSF and MEE water desalination plants. On nuts and bolts used for holding plants to foundation exhibited crevice corrosion due to dust and seawater mist accumulation. White color deposits with the bluish and green tinge were observed under and adjacent to tube supports and partition plates, even embedded in crevices and adhered at discrete spots on external tube surfaces, well away from tube supports and partition plates as shown in the slides. Right, when it will agree to their slides, that will clearly shows what we are talking about. This slide, the continuation of previous slide, shows the locations of crevice corrosion as observed in thermal MSF and ME water desalination plants. White color deposits were also noticed on walls of flashing chambers, demisters, and in gaps between shell wall and demister during inspection. Deposits were mainly carbonates. Originally, the brine press system was made from copper nickel 9010 header with vertical nozzles, focusing brine spray on tube bundle as shown in the coming slide, which is actually slide number 68 of the overall presentation. But we'll come to that slide. That slide explains what we are talking about. Threaded brine spray nozzles were introduced locally as a part of ease and quick replacement strategy when the original welded configuration served its design life. This slide is a continuation of the previous slide where we said that the slides will come which shows the exact location of the crevice corrosion in ME water desalination plants. The crevice corrosion was observed at the threads of the brine spray nozzle system. The brine spray nozzle system was made from copper nickel 9010 and was modified to threaded system for the easy replacement. This slide is a continuation of previous slide, shows the location where crevice corrosion was observed in two modules long tubes MSF WTP. It shows the crevice corrosion is so bad and it has perforated right under tube supports from stage 1 to stage 12 in two modules long tube MSF plant. This slide is a continuation of the previous slides. It shows the causes of crevice corrosion as observed in thermal two modules long tube MSF water desalination plant. The high degree flashing in flash chambers that causes the high degree of crevice corrosion. Accumulation of carbonate deposit at discrete locations. Use of threaded brine spray nozzles. Accumulation of dust and seawater mist at nuts and bolts in foundations. This is the last slide of the part 2 of the experience observed in water desalination plants corrosion. This slide shows how to control the crevice corrosion in thermal two modules long tube MSF water desalination plant. Fabricate chain bushings, rollers and pins from Inconel alloy 625 of hardness 190 HB or Stainless steel with higher molybdenum content, avoiding stagnant conditions for crevice control. Revert to original welded configuration of brine spray nozzles to overcome crevice corrosion at threaded joints.